we have a gassy lab, pretty fun. So again, continuing our, like I mentioned before, we're going to basically be doing labs that we had to skip over that now we can do. And next week's labs are going to be so cool. And you might notice if you looked at my schedule that I posted online, today we're doing the gassy lab, and then on Thursday or Friday, then we're doing the H2 pop lab. So those of you who are in the other come to school cohort can do another lab. It's very similar to this one, not the same, but it's very similar. And then next week, we're going to repeat the lab for both sessions because you're going to make something you can take home that's super, super cool. So I want to make sure both cohorts get a chance to make that. And if you're in cohort C and you want to join us for the lab, well, it'd be really cool if we got that safety sheet in. I'm not going to worry about it, but I've said my piece. All right, so what we're going to do today is we're going to pass a mass of a gas through a glass in class, and then we're going to measure the mass of the gas that we pass through the glass in class. And what we're going to be using is graduated cylinder because we don't use glass graduated cylinders anymore. When I was your age, we used glass, and we broke one every single week. We break this, it just a little piece falls off. The glass doesn't go everywhere. And then the gas that we're going to be passing through the class is butane out of a handy little butane gas container, like so. It's pretty neat. And so let me show you what we're going to be doing. I'm going to be moving the camera. Sorry for you at home. There we go. We're going to get our goggles. And for those who are in class, goggles are in the cabinet over there. When you are done with your goggles, we're going to bring them up here, and you're going to set them up here to be sanitized. Next year, students are going to sanitize their own goggles, but we'll set them right here to be sanitized. And then, yeah, so I've got my goggles on, and we're going to use a technique called water displacement. So I'm going to fill up this tub full of water, or half full or 3/4 full, and then I'm going to put my graduated cylinder under the water and invert it so it's totally filled with water. Then I'm going to take my gas canister, and I'm going to go under it and pull the trigger, and gas is going to come up and displace the water, hence water displacement. And I can use the volume here to know exactly how much gas I've actually collected. So when you guys are doing it, you're going to do it in the sink like this. So I'm going to bring it up so people in the camera can see, and you can see too. Yep. Okay, so the graduated cylinder goes into the water like so. And then let's get some of these bubbles out. Yeah. All right, so now you have all this water right here. And I'm going to take, yes?
The camera should be tilted down a bit. Camera, see what you're doing.
Oh, because it's cut off?
Yeah.
Keep forgetting that Google cuts off about, thank you. I keep forgetting Google cuts off about like 20% of what's on the screen. Is that better?
Yeah.
All right, thank you. All right, so you got a column of water, and you're going to put your gas canister under the water and pull the trigger. And there it goes. And some of these gas canisters, if this is a good test to make sure it's working. If it doesn't go very fast, you can just chuck it and get another one, or open it up. I can show you how to open it up a little more. But there you go. So you're going to dispense gas. You're going to pass the gas through the glass in class until you get about 100 milliliters. Okay. Now, rather than go the 100 milliliters, so once I do that, it's going to fall over. I'm going to show you the calculations we're going to use. And the calculations we're going to use is the ideal gas law, which is PV equals NRT. Pivner. Oh, I'm right in the glow zone, huh? Deal with it. Anyway, so PV equals NRT. And we're going to use the volume of the gas we collected as V. So, and it's probably going to be the easiest thing to always collect 0.1 liter or 100 milliliters. So we're going to collect 100 milliliters, and that's, yeah, I know. It's going to be 0.1 liters. Okay, so we're going to collect 0.1 liters. And then the pressure here, it's a normal day. It's not, there's not a thunderstorm. So we can basically say the pressure is most likely 1.0 atmospheres. Pretty safe bet because there isn't a thunderstorm, nothing's falling, there's not a tornado. So 1 atmosphere is probably the pressure. And then R, since we're using atmospheres, is 0.0821. So far so good? Okay. Now temperature, we're going to assume that the temperature in the pipes is about the same as what it's in the air because pipes are pretty big. My thermometer tells me it's 21 degrees. If you want to get a very specific measurement, you can drop one of these into the water. This one also says 21 degrees. So it's 21 degrees, but do we use degrees Celsius in temperature? No, we never do. We use Kelvin. So take the 21 and we're going to add 273. So the temperature at this point is going to be 294 Kelvin, which leaves us one variable to solve for. And that is the number of moles, solve for moles, the number of moles that we pass through the container. Make sense? Now we're going to compare this to grams. So we're going to eventually we want molar mass. We want experimental molar mass. And molar mass has the formula gram per mole. Well, this mole will give us the mole part. The gram part is we want to know what the mass was of the gas we passed through the glass in class. How might we figure out how much gas in grams we dispensed? Any idea? Homies in class? How can we figure out how many grams of gas we dispensed? Where'd the gas come from?
Oh. Yeah.
So what would you do? Wheels are turning. If I wanted to figure out how many cashews my son ate, or how many the grams of cashews my son ate from the jar, how might I figure it out? I could count all the cashews that are left, or I could weigh the container beforehand and weigh the container afterwards. We're going to do the same thing with the gas canister. We're going to weigh the container before we dispense gas, and we're going to weigh the container after we dispense gas. But there is a catch. The catch is the container is going to be wet, and we're not going to be able to remove all of the water. So what we're going to do instead is we're going to do a technique so there's about the same amount of water on the container every single time. Make sense? This is how you do it. Turn on your balance and make sure your balance is dry, and then you're going to get your gas canister wet, and then consistently, you know what consistently means? Okay, consistently, you're going to go 180 degrees, same way, and wait. So my current weight is 11.71 grams. So we're going to record that. So M1 is 11.71 grams. Then we're going to conduct the experiment. So put it underwater, dispense our gas. Bubbly, 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 bubbly. And some of these can actually be hacked a little bit. You can actually really open them up. Here we go. Yeah, blub, 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 blub. And again, the lab says collect between 90 and 100 milliliters. To make the math easy, just collect 100 milliliters. That way the volume is 0.1. Getting there. And if your gas canister goes really, really slow, give it to me so I can throw it away. I just want to make sure that the valve is not obstructed and then give it me away. I get them four of them cost about $3. All right, so I got 100 milliliters of gas in here. All right, same thing as before. Oh, that's gonna fall over. Okay, let's do this. This last part is optional. It's pretty fun though. Butane has a molar mass that is larger than 29. So 29 is the molar mass of the mixture of oxygen and nitrogen that is air. So butane is bigger than that. It's 58. So that means butane is heavier than air. Meaning, if I pick this up, the butane is going to spill out over the water. So this next part, totally optional, but kind of fun. you get yourself some fire. Fire's right over there. Get yourself some fire, and then you can actually pour your butane out over the water. You can light it on fire if you want to do it. Don't have to do it, but if you want to do it, it's fine. All right, so there you go. Now we need to find out what my ending mass is. Once again, I got a wet container. I'm going to go up 180 degrees and wait. And now my new mass is 11.52. So M2 is 11.52 grams. So far, so good. So now we have a change in mass, which we can put in to find grams, and we got our moles, which we're going to put in to find moles. So we're going to do trial 1 together, and trials 2 through 4 you're going to do. Make sense? Okay. I'm going to give myself some more. I'm going to make this come back up so I can actually use the top of the board. There we go. All right, so let's go ahead and put our numbers in. 0.1 or 1.0, 0.1, I'm going to solve for that. 8.0821 and 294. So we're going to solve for n. And when you solve for n is going to look like this. It's going to look like n equals PV over RT. So for experiment 1, it's going to be 1 times 0.1 divided by, open parentheses, 0.0821 times 294, close the parentheses, and I get 4.24 times 10 to the negative 3 moles, or 0.00424 moles. And this moles is what we're going to put in down there. Oh, is it 0.0, extra 0, 10 to the negative 4. There we go. 4.0000424. There. So negative 4. All right. So far, so good. Okay. Next, we're going to do the change in mass. And the change in mass here, so the delta M is going to be 11.71 minus 11.52, and 11.71 minus 11.52 is going to give us 0.19 grams. So we dispensed 0.19 grams of gas through the glass in class. Now we can find our experimental molar mass. And our experimental molar mass will be just those numbers. So that number is going to go right there. And this is going to be 0.19 divided by 0.00042. 0.19 divided by 0.00042. It can't be right. I must have, yeah. This is actually exactly what I thought it was. 0.3. I think I made a mistake in that one. So I'm going to do the math again. So 0.1 divided by 0.0821. I think I forgot a 0 in there. See, even adults make mistakes. That was 294. Yes, that's what it should be. It should be 0.0041424, and 4.2 times negative 3. There we go. So yeah, thought I had the right originally. 0.00424. So 0.19 divided by 0.00424. That gives me 44.8 grams per mole. 44.8 grams per mole. So this is my experimental molar mass. The molar mass according to my experiment. Are you with me so far? Okay. Now, the last thing we need to do is what's called an error percentage. And an error percentage is something that compares your experimental value to a published value. To basically, it's basically your quality of your data. And the error percentage works like this. How much? Got some space down here. How about down here? I also have space up top. I'll look here. So error percentage, percent error, is the ideal value minus the experimental value over the ideal value multiplied by 100%. Now, what is the ideal value? Well, the gas we're using is C4H10, butane. So butane has 4 carbons at 12 each. So 4 times 12 plus 10 hydrogens at 1 each. 10 times 1, which is a grand total of 58 grams per mole. 4 times 12 is 48, plus 10 more is 58. So the ideal value is 58. So to figure out my error percentage, I'm going to take 58 minus my 44.8 divided by 58, multiplied by 100% in parentheses, or in absolute value. So my data, let's see how good my data point was. 58 minus 44.8, enter, divided by 58. I got 22.7, 22.8. So 22.8%. Okay, that's my error percent. So that is basically how good my data be. Make sense? All right. So what you're going to do is we're going to form 2 groups. We're going to form 2 breakout rooms. And those of you at home are going to be in charge of the math. And those in class are going to be in charge of the hands and the feet and the eyes and the nose and everything else. Okay? So people in class, don't let the people at home con you. They're doing the math. Okay? That's their part. So we're going to break up into 2 groups. And then in just a second, you're going to do the lab. Those in the class, you're going to gather up a tub of water and a digital balance. There's a digital balance over there. There's one in a bunch of drawers. One group you need to work up here if you want. You're going to need a graduated cylinder and a gas canister, and that's it. If you want to use a thermometer for the temperature, you just drop it in. Then you'll have a very precise value that you know exactly what the temperature of the water is, because the temperature of the water is going to be the same as the temperature of the gas coming through it. But again, once it's been in the room for a while, it's pretty much the same as the entire room. All right, so I'm going to, okay, first of all, any questions at home or in class? Yeah.
I'm going to the safety sheet sign.
Don't worry about it. I will ask you to tie your hair back though. And if you need help, there's tools in the goggle cabinet. There's crimpies and crampies and cloppies and clippies and all the other things you guys use in your hair. So yeah.
The gas constant's just going to say 0.0821 the whole time, right?
Yes. Yeah. It's a gas constant, and it's based on the pressure we use. As long as we're using atmospheres, R will always be 0.0821. Okay, good question. Any other questions? All right. And again, fire, totally optional, but a lot of fun. So you do need to wear glasses. You need to wear glasses in the entire lab. I'm going to go set the breakout rooms up. I'm going to make 2 breakout rooms. And everybody needs to open rooms. So everybody needs to join a breakout room. So go ahead and join a breakout room, and we'll make sure there's at least 2 in-class people in each room. If not, I will edit the rooms. And then I will mute my mic. So once you guys are in your breakout rooms, you can talk to each other through one of your laptops. I will mute my mic so there's no crazy feedback. Okay, Alyssa and Bryant are not here. All right, so Cheyenne's in group 1 and group 2. Okay, I totally apologize. I haven't learned a lot of your names. So you are Peyton and you are Lily? Okay, so Lily is in group 1. So group 1 is good. And in group 2, there is Hunter is in group 2, and Roland's in group 2. And Peyton, you must also be in, are you in the room? Oh, you're in group 2. Okay, cool. Hey, Brett, we are in breakout rooms. So I'm going to edit rooms and put you in a room. Edit rooms. You are now in group 1. Okay. and save. All right, so we got at least 2 people in each breakout room. Again, homies, you need to work with your in-class students, and you're gonna be doing the math part of it, and your in-class people will share what they're doing. Okay, last question, any questions? You can ask questions in the lab, obviously, too. Okay, I'm going to stop recording, and I'm gonna turn the camera around, and you guys can work on